In this lecturing video, we will introduce several variations of neural network. Until now, we have already introduced the structure of a deep neural network. However, all the instances we introduce are the fully connected neural network. But actually, there are many variations that can be used to different applications. And according to the domain we are working on, we may be able to develop a different structure to more efficiently describe the data we analyze. And in the following, we will mainly introduce two variants of the neural network. The first one is convolutional neural network, or CNN in brief. This network structure is widely used in image processing because this structure has many interesting properties. And we will also introduce the recurrent neural network, or called RNN in brief. So let's talk about CNN first. Why do we use convolutional neural network for image analysis? Okay, so let's think about the problem. When processing image, the first layer of the fully connected network would be very large. So if we use fully connected network to describe an image, this is a problem. Assume that the input image, the resolution of the input image is 100 by 100. So how can we represent this image? So basically, we represent these images by an 100 by 100 dimensional feature vector if this image is a gray label image. And if this image is a colorful image, we have to separately describe red, green, and blue. So the dimension is even higher. Okay, so assume this is a colorful image, and the input layer should consist of 100 by 100 by 3. So this is a very, very high dimensional feature vector. And if we consider the fully connected network, then assume that the second layer consists of 1000 nodes. Then we can calculate that there are 3 times 10 to the power of 7. There are so many weights that to be determined between the input layer and the first hidden layer. Okay, so this is just the numbers of weights between these two layers. And if we have several layers, you can imagine how many weights we should estimate. Okay, so if we use fully connected network to describe an image, we need to estimate many weights. Okay, in this deep framework. So the question is, can we simplify the fully connected network by considering the property of image recognition so that we have much fewer weights to be estimated, and at the same time we can also achieve good performance. So this is the problem. To simplify the deep network, we talk about image property first. In image recognition or image analysis, some patterns are much smaller than the whole image. For example, if we want to detect the beak, okay, the beak, that is the mouth of the bird, okay, and basically a neuron does not have to see the whole image to discover this pattern. So in image recognition or image analysis, we usually need to discover some specific pattern. However, this pattern does not appear all over the whole image. We just need to consider part of the image. Okay, and if we can consider just a region, a sub-region of the whole image, we can connect to this small region with less parameter. So for example, we can for this node just consider the input smaller region, and based on this smaller region, the numbers of weight to be estimated can be reduced significantly, because right now for this small region, if we transform this region into a feature vector, the dimension of this small region is much smaller than the whole image. Okay, so this is the first observation. The second observation is that the same patterns may appear in different regions. For example, in these two images, the beak may at the left top, or the beak may appear at the center of the image. Okay, so it's not necessary to use one node that specially detect the upper left beak, and another node to detect the middle beak. Actually, the function of these two nodes should be very similar, and we may just use one node. Conceptually, we may just use one node to detect the beak. Okay, no matter this beak appear at the left, at the upper left, or appear at the center of the image. Okay, so these two nodes do almost the same thing, and they can use the same set of parameter. Okay, so conceptually, the parameters they use can be the same. So we can, because they are redundant, so basically maybe we can just estimate one set of them to accomplish the task we want to do. So this is the second observation. The third observation is that subsampling the pixel will not change the object. For example, for these two, basically the content of these two images are the same, and this image is high resolution, this image is in low resolution, but we all can easily recognize this is a bird and this is also a bird. So subsampling does not change the concept or the semantics of the image. Okay, so we can subsample the pixel to make images smaller, and as the image becomes smaller, the dimension of the feature description can be largely reduced, so that we can reduce, we have less parameters to be estimated. Okay, so through this observation, we can design a new network structure where we can use much fewer weights or much fewer parameters to describe image information. So the whole convolutional neural network, the idea is this: given an image, we can do convolution. Okay, convolution is a quite common operation in signal processing. Okay, and we will go into the detail of convolution later. So we can do convolution, and then we do max pooling. Max pooling is basically for subsampling. Okay, and then we can do the same thing several times. We can do convolution again, and then max pooling, and repeat the same procedure several times. And then we flatten it. Okay, we flatten the feature vector, and then input the flattened feature vector into a fully connected feed-forward network, so that we finally can recognize the semantics of this image. Okay, so basically the convolution and the max pooling, this part is for feature extraction, and the fully connected part in this framework is for classification. So this is for feature extraction, and this is for classification. So corresponding to the properties we mentioned above, convolution is for the property 1 and property 2. Okay, property 1 is some patterns are much smaller than the whole image. Okay, so we can just use a window. We can just use a sliding window to do the convolution, and this sliding window may corresponding to the pattern that may appear much smaller than the whole image. And also, the same pattern may appear in different regions. So, as we say, we use a sliding window to do the convolution. And this sliding window may appear in different regions of the whole, inside the whole image. And for max pooling, that is corresponding to the third property, subsampling. Subsampling will not change the object, will not change the semantics of the object. Okay, so this is the idea of convolutional neural network. So first, we will introduce the convolution operation. Assume that we have a 6x6 image, and right now the intensity value of this image is either 1 or 0. Okay, so this is a very simplified example. And in this image, basically it is a black and a white image. Okay, and assume that we now use two different kinds of filter to do convolution. Okay, and for the first filter, it is a 3x3 matrix or a 3x3 window, and the pixel value corresponding to the diagonal will be multiplied by 1, and the pixel out of the diagonal will be multiplied by -1. Okay, and this is the first filter. And the second filter is the pixel in the middle column will be multiplied by 1, and the pixel out of the middle column will be multiplied by -1. Okay, and this is the second filter. And we can also define many other filters to do convolution. And in fact, the parameter inside each filter will be learned automatically by the deep learning framework. Okay, and each filter detects a small pattern. We can imagine that each filter detects a small pattern. For example, the first filter detects the diagonal pattern. The second filter detects the vertical pattern, and so on. Okay, so corresponding to the first property, we see that we don't need to consider the whole image to detect some specific pattern. In this case, we just consider a 3x3 region to detect a specific pattern. Okay, so how can we do the convolution? Let's take the first filter as an example. We just apply this filter on a 3x3 region. Okay, for example, at the upper left corner, we apply this pattern. We apply this filter on that. And because the value along the diagonal is 1, 1, 1, and the value out of the diagonal is 0, 0, 0. Okay, so we multiply the value 1, 1, 1 by 1, 1, 1, and then we got 3. And then the value out of the diagonal are all 0. We multiply them by -1, and then we combine them together, and finally we get the value 3. So this is the response of the convolution of the first region. And right now, if we set the stride of the convolution as 1, that means every time we finish this convolution, we move 1 pixel to the right and then do another convolution. So this is called stride. The stride is the interval we do the convolution. So right now, if we set our stride as 1, we do the second convolution. Okay, that means we check the pattern at the second subregion. And right now, we multiply 0, 0, 1 by 111, and then multiply this value and this value by -1, and then sum them together, and finally we get the value -1. And we can repeat the same process through the whole image. Okay, and this is the case of the stripe. If we set the stripe as 1, if we set the stripe as 2, so the same. For the left top corner, we get the value 3, and then we move 2 pixels to the right, and then the second output will be -3, because right now we multiply the diagonal pixels by 1, and the pixel out of the diagonal are multiplied by -1, and finally we got -3. Okay, and so we can get different result if we set different stripe. Okay, and in the following we will take the stripe setting as 1 as the main example. So when we set the stripe as 1, we can go through the whole image, do all the convolution, and then we get this result. So the first result is 3, and then -1, and then -3, and then -1, and so on. And then when we go through the first horizontal case, we then move the window in this case. Okay, and in this case, we also get the result -3. Okay, because we multiply zeros by 1, and then multiply these values out of the diagonal by -1, and then we get the value -3, and so on. So if we go through the whole image, we can get this result. And basically, because of the numbers of stripes, we get a 4x4 result. You can see that. So the original image is 6x6, but right now we get a 4x4 result. Okay, and we can also observe the value in this 4x4 result. We see that at some place, at some position, the result is larger. At some position, the result is quite small. Okay, let's check the result, the large result here and here. Actually, at the left top corner, because the pattern of the left top corner is exactly the same as our filter. Okay, our first filter is used to detect the diagonal pattern, and the left top corner has such pattern. So we can see it has a large filter response. That's 3. And also we can see at the left bottom corner, it also has such diagonal pattern. So we have a big filter response corresponding to this corner. On the other hand, for the pattern at the right top corner, it has an inverse pattern to the first filter. Okay, so we can see a very small value. We can see very small value at this part. Okay, so according to the value of the filter response, we can imagine whether a subregion corresponding to a filter or not. Okay, and this property also corresponding to the this characteristic also corresponding to the second property. The second property is that similar pattern may appear many times in the whole image. Okay, so in this case, the diagonal pattern from the left top to the right bottom, this pattern appear at the left top corner and the left bottom corner. So we can see the filter response are big at the left top and the left bottom. We can apply the same process based on the second filter. Okay, so again, we can apply this filter to do convolution, and go through the whole image, we can get another 4x4 result. Okay, so based on different filters, we can get different filter response, different filter result, and all this 4x4. So based on one filter, we can get a 4x4 result, and based on another filter, we can get another 4x4 result. And basically, these 4x4 result are called feature map. Okay, so basically, the feature map are filter response of the whole image when we do the convolution. And you can see that the dimension of the feature map is different from the original image. The original image is 6x6, but the feature map is 4x4. And if you feel unhappy about this, you want to make the dimension of the result exactly the same as the input, then you can do zero padding. Okay, that is if we virtually think that the value of the pixel outside the image are all zero, and then we can pad in this value as 0, and then we can apply the same filter to do convolution. We start at the first point. We start at the first pixel. Okay, that means we virtually have we virtually do convolution for this subregion, and this region is centered at the first pixel of this image. Okay, so in this case, if we set the numbers of strike as 1, we can get a value here, and then we can get a value here, we get a value here, and finally we can get 6 output value for the first row. Okay, so by this way, we can get a 6x6 feature map. Okay, we can get a 6x6 feature map, so that the dimension of the feature map is the same as the input image. Okay, and you can consider this alternative to do your work. Okay, zero padding is not necessary, but sometimes it helps, sometimes it doesn't. So that the decision, the setting of zero padding or not, depends on your application. And in previous example, we just consider the black and white or gray level image. However, when we handle a colorful image, for each pixel we have 3 channels: red, green, and blue. So how can we do that? The solution is simple. We just apply this convolution for the red channel first, and then for the green channel, and then for the blue channel. So, for example, for the red channel, we will have 2 different feature map. For the green channel, we will have another 2 feature map. For the blue channel, we again have 2 feature map. So finally, based on 2 filters, we have totally 6 feature map. And then we use this 6 feature map to do the following process. Okay, so the same process can be done for colorful image. We just repeat it. We just separately do it for different color channel. So after describing the convolution operation, we now go into the detail of max pooling. Max pooling is to do subsampling. So based on the feature map, we can consider, for example, a 2x2 subregion of the feature map, and then find the maximum value of this 2x2 subregion. For example, in the first subregion, the maximum value is 3. So we only we only retain the value 3 after mass pooling. For the second subregion, we just retain the value 0. For the third one, we retain 3. For the fourth one, we retain 1, and so on. And also, based on the feature map generated by the second filter, we also do the same process. So the whole process is that given the input image, we first do the convolution based on some filter, and based on the feature map, we do mass pooling. Okay, so finally, we get a 3, 0, 3, 1 based on the first feature map. We get -1, 1, 0, 3 based on the second feature map generated by the second filter. So we can view this result as a new image, but smaller. Actually, this 2x2 image is a subsampling version of the convolution result. Okay, and we can view each channel, each filter as a channel. Okay, as a channel, and for each channel, we can get a new image, and this new image, the dimension of this new image is even smaller than the dimension of the feature map. So go back to the whole framework. Given an image, we do convolution first and then do mass pooling. And after mass pooling, we can think that the result is actually a new image. Okay, we have already transformed, or we have already embedded the original image into a new image, and such new image has fewer dimensions. Okay, and based on this new image, we can do convolution and mass pooling again. Okay, so we can get smaller and smaller. Okay, the new image is smaller than the original image, and the numbers of channel is the numbers of a filter. So although we have only one original image, but right now, depending on the numbers of filter, we have several new image in lower resolution. Okay, so in the whole convolutional neural network structure, we do convolution and then mass pooling, we get a new image, and based on this new image, we do convolution and mass pooling again, and we get newer image. And after repeating this process several times, we finally flatten the result, and then input the flattened result to the fully connected feed-forward network. So how can we do the flattening? Assume right now we have two new images. Okay, this is actually the pooling result of the feature map. So we have 3, 0, 3, 1, -1, 1, 0, 3. How can we do flatten? Flatten is actually simple. We just go through all the result of this feature map. So we get 3, 0, 3, 1 as the first part. And then we got -1, 0, 3 as the second part. And then we concatenate this result as a vector. And we input this vector into a fully connected neural network. And this part is for classification. And the 3, 0, 3, 1, -1, 0, 3, these are actually the extract feature from the original image based on concatenation of different filter response. Okay, so let's revisit the whole idea. So given the input image, we do convolution and then do maxima pooling. So this is the convolution part. And for maxima pooling, assume we have 5 and 7, and then after mass pooling we have only 7, and then this part we have only 1. Okay, and this structure is actually has been introduced previously. Okay, this is actually a mass out network. So you can see that the convolutional neural network is actually a special case of max out network. And this is another illustration showing the idea. So the original image is here, and then we do convolution, and then we do max pooling. So finally, we can get the final feature. We only represent the original image, as 7 and 1. And in this part, we ignore the nonlinear activation function after the convolution. Okay, but actually, we can do, depending on the design of the filter, we can also do nonlinear activation after convolution. We can also do that. So why the convolutional neural network can largely reduce the numbers of parameters we need to estimate? Let's go back to the example we introduced. So given this 6x6 image, and if we apply the first filter, this is a 3x3 kernel, and we just do the linear combination of the pixel value of the upper left corner. Okay, so after the convolution process, we finally get the result 3. Okay. And let's go into the deep detail of this calculation. Basically, the first pixel multiply 1, the second pixel multiply -1, the third pixel multiply -1, and this is 4, 5, 6, and the 7 pixel multiply -1, the 8 pixel multiply 1, and so on. So if we just flatten the 6x6 image, we can see it's actually a 36-dimensional vector. And in the first convolution, we only conduct process on the first, second, third, 7, 8, 9, 13, 14, and 15. Okay, and basically the parameter to multiply these 9 parameters are these 9 values. Okay, they are 1 or -1. Okay, so only in this convolution process, we only connect to 9 input, not fully connected. Okay, so this is totally different from the fully connected network. In the fully connected network, for each pixel, we have a weight, we have a parameter. Okay, we have an edge connecting the input and the node. Okay, but with convolutional neural network, we only connect this 9 pixel to this node at the first convolution. Okay, so we need much less parameter to do the convolution. And if we move to the next window, we move to the next subregion, we found that in this case, we multiply the parameter. We multiply the pixel value of the second pixel value, third pixel value, and the fourth pixel value, and the 8th pixel value, the 9th, the 10th pixel value, and so on. So in this case, again, we only connect this 9 pixel to the next node. Okay, and we see that basically the parameter connecting the first pixel and the first node, and the parameter connecting the second pixel to the second node, these two parameters are actually the same. You see that they are all in dark red. Actually, they all corresponding to +1. And the parameter connecting the second pixel to the first node, the parameter connecting the third pixel to the second node are actually the same. Okay, we mark it in red here. And these are both corresponding to -1. So we see that although we do many convolution process, but the parameter to do such convolution are all these 9 parameters. Okay, so we share weights across the convolution process over the whole image. Okay, so this characteristic make the CNN structure needs even less parameters. Okay, so this is why we can largely reduce the numbers of parameters we need to estimate in CNN. And this is totally different from the fully connected network. So now we have already introduced the structure of convolutional neural network. And let's recap the general idea of constructing a deep learning framework. The step 1 is to define the network structure. And now we have finished this part for the convolutional neural network. The second step is to define the goodness of a function. Okay, and the third step is to pick the best function. And basically, even if you use CNN, the goodness of function, the measurement, the way to define the goodness of a function are similar to that of fully connected network. Okay, so we can use cross entropy, we can use mean square error, and so on. And for the third step, how to pick the best function, and basically nothing special, just again the gradient descent algorithm. So for the second step and the third step, even if we use convolutional neural network, we also use the same technology to find the best function. Okay, although we may change the network structure from fully connected network to convolutional neural network. And you may wondering that in the summer of 2016, AlphaGo, the AlphaGo system beat the champion of human, okay, in playing Go. Okay, so you may wonder how deep learning can be used to play Go. Okay, so how can we develop a system based on convolutional neural network to play Go? Okay, so we can imagine that in Go, in the game Go, actually it is a 19 by 19 matrix. So we can view the plate as an image, and we can view the black item as 1, the white item as -1, and then if no item on a position, we say that this point is 0. So we can view this plate as an image, and we can input it into a deep network, and then this network output the next move. That means which position you should place. Okay, you should place which position you should occupy. Okay. In this work, we can use fully connected feed-forward network. We can use that, but CNN performs much better. So actually, we can use convolutional neural network to play Go. So the idea is we also input the plate. We transform the plate into a vector, and then we use CNN. And finally, this CNN structure output the target. That means the position. Okay, that output the best position you should place. You should occupy in the next move. But why CNN can be used to play Go? Okay, there are some observations. First, some patterns are much smaller than the whole image. Okay, so if in playing Go, we actually usually see many local patterns. Okay, and this is quite similar to the characteristic in image object recognition or detection. And actually, in the system AlphaGo, they use 5 by 5 pattern for the first layer. The second observation is that the same pattern may appear in different locations, just like in this pattern. This pattern may appear here, may appear here. Okay, so this again is appropriate to be modeled by convolution. And in the CNN framework we introduced before, every time given an image, we first do convolution and then do mask pooling. Okay, and mask pooling is used to subsampling, to subsampling the input data. Okay, in image recognition, subsampling does not change the object. However, in playing Go, can we use subsampling? Can we use mask pooling? Actually, AlphaGo does not use mask pooling. So this is a part of the AlphaGo paper. We see that they use 19 by 19 by 48 image state consisting of 48 feature plane, and then they do zero padding. And the convolution kernel is 5 by 5 with stripe 1. And they have the subsequent hidden layer 2 to 12. Okay, and then actually they don't use mask pooling, so they don't subsampling the given the input image. Okay, so we can from this example we can also understand, we can also realize that actually there is no standard to apply or to design the deep learning framework or the convolutional neural network. So we can modify the structure according to the target we are working on. So now we have finished introducing the convolutional neural network. In the next slides, we will introduce recurrent neural network, which is also very important in recent studies. Recurrent neural network was designed to make the deep learning framework to have memory, and to state why the deep learning framework should have memory, we use an example application to mention this. Okay, this application is called slot filling. Okay, so imagine that you have a ticket booking system, and a user call the ticket booking system, say, I would like to arrive Taipei on November 2nd. And the so-called slot filling problem is we want to identify which word corresponding to destination and which words corresponding to the time of arrival. Okay, so it is the problem that we try to identify the meaning of each word in this sentence. So this is called a slot filling application. And can we use slot filling? Can we solve slot filling by feed-forward network? Okay, so the idea is, yes, we can input a word. Okay, and we can transform each word by as a vector. Okay, and given this vector, we develop a feed-forward network, and finally, it may output the probability of this word, the given word, belonging to some specific concept. For example, the Y1 represent the probability of the given word represent time. The Y2 represent the probability of the given word belonging to the destination, or maybe the source. Okay. So in this case, we need to transform each word into a vector first. And how can we represent that? How can we represent a word as a vector? Okay, actually there are several methods to do this. One of that is one of n encoding, or sometimes it called one hot representation or one hot encoding. Okay, the idea is assume we have a lexicon. For example, we have a lexicon or dictionary where consists of apple, bag, cat, dog, elephant. Okay, and we can represent apple, the word apple, as 10000. Okay, we can represent bag as 01000, and so on. And we can see this in this vector, only one dimension is unity, and other dimensions are all equal to 0. Okay, and the length of the vector is actually the lexicon size, and each dimension corresponding to a word in the lexicon, and the dimension of the word is 1 and the others are 0. So this is the simplest representation of a word. We can use one of n encoding. We can also consider more variants, like because there are so many different words, so we may not be able to define all words in a lexicon. So there may be a dimension specific for other. Okay, the other means the words that don't exist in the lexicon. So, for example, Gandalf or Sauron, they all belong to the other dimension. Okay, so we can do some modification. We can also consider another method called word hashing. That is, for example, the given word apple. We can check the consecutive 3 letters, and to construct a big hashing structure. Okay, so for example, apple, the first 3 letters are app. So in the dimension corresponding to app, we denote it as 1, and then it's ppl. So in the dimension corresponding to ppl, we have 1, and in ple we have 1, and at other place we have 0. So in this kinds of vector, the first dimension corresponding to AAA, the second dimension corresponding to AAB, and so on. So actually, the dimension of such representation is 26 by 26 by 26. Okay, so this is another representation. So when we transform a word into a vector representation, we can input this vector into a feed-forward network, and the output, for example, y1, corresponding to the probability of destination, y2 corresponding to the probability of time of departure. But what is the problem of such network? Okay, we can see these 2 examples. A user may say, I would like to arrive Taipei on November 2nd. But another user may say, I would like to leave Taipei on November 2nd. So if we just transform an individual word into a vector, basically this is the word Taipei. This is the same word Taipei. However, the word Taipei in the first sentence means the destination. The Taipei word in the second sentence means the place of departure. Therefore, if we just consider an individual word, we cannot really identify the semantics of such word. Okay, so this is why we need a neural network that has the probability to describe memory. We have to know the previous word is arrive. When the previous word is arrive, then this Taipei means destination. When the previous word is leave, then this Taipei is actually the place of departure. Therefore, we need the memory characteristic. And this is why the recurrent neural network was designed. So let's go recap the 3 steps of constructing a deep neural network. So the first step is to define the structure. Okay, and here we introduce the recurrent neural network, or RNN in short. Here is the basic idea of RNN. So given the feed-forward network, so input is a vector, and then we can, through the process of many layers, we can calculate the result. But the output of the hidden layer can be stored in the memory. So assume we have several memory node, and then the output of this hidden layer can be stored into this cell. Okay, and at the next time when we go through this network, we can read information from this memory, and then the information from the memory as well as the new input information can be considered simultaneously to generate the next output. Okay, so memory can be considered as another input. So at the next time when we at this node, we will consider the input information as well as the information from the memory node. Okay, so memory can be considered as another input. This is the basic idea. So let's go back to the slot feeding application. The first word, arrive. We transform this word as a vector, and then we input it into a hidden layer. And the result of this hidden layer is A1. Then we store the A1 into a memory cell. And based on the A1, we can also do the following process and may output the probability of arrive in each slot. Then the second word, type A, we transform this word into a vector, and we input this vector into the hidden layer. At this hidden layer, it will consider the information from X2 as well as the memory stored previously. So it will also consider the information from A1. So consider the information of A1 and X2. This hidden layer output result A2. And based on A2, we can do the following process and output the probability of type A in each slot. And then remember, the result A2 is also stored into a memory cell. Then the third word come in. It is transformed into the vector X3. And at this hidden layer, it jointly considers the input information S3 and the memory information A2 to output the result A3. And then input the A3 into the following process to output the probability of R in each slot. And the same network can be used again and again along with the sentence. Okay, so this is the idea how we consider information from memory and how can we make a deep learning framework to have memory characteristic. And because we have memory, so if there is a sentence called leave type A and another sentence state arrive type A, the information stored at this memory cell and at this memory cell is different. Okay, so the value stored in the memory is different because the first word of the sentence here is leave. The first word of the sentence here is arrive. So the information stored at A1 is different. Okay, so that we may be able to output different result, although the input word are all type A. We may have different output at Y2. Okay, so this is the this is why RNN can be used to do better slot fitting. And of course, the whole framework can be deep. Okay, so in previous slides we just show one hidden layer. Actually, we can have many hidden layers, and for each hidden layer, we can have many memory. Okay, for each hidden layer, we can have its memory structure. Okay, and the memory can be input to the next hidden layer at the same level, or maybe at different level. And actually, we can also have many variants. Okay, so one variant is called bidirectional RNN. So in previous slide, we just consider the information from previous words, but actually we can also consider information from the following words. So given the input xt, at this hidden layer, it will consider the previous memory and then output. We can also input this word into another hidden layer, but at this hidden layer, it considers the information from the memory derived from the following word, and then make output. And then by jointly consider these two information, we finally output the result for xt. So we consider the memory information from left to right and also from right to left. And this is called bidirectional RNN. And this is quite common when we try to describe a sentence, because to understand an individual word in a sentence, we may consider the whole context. That means we need to consider the word in previous and the word in the following. In implementing RNN, how exactly do we implement the memory cell? Okay, one of the most standard way to implement the memory cell is called LSTM, long short-term memory. Okay, so how can we do that? Assume that we now have an input signal. Okay, and we have an input get to control whether the input signal can be considered, and there is a signal coming from the outside of the memory cell. Okay, there is a signal to control the input gate to determine whether the input gate can be open or not. Okay, and then if the input gate is open, then the input signal can be input to the memory cell. And originally, there should be some information in the memory cell. We will process the input information and the memory information. However, there is a mechanism that is called forget. There is a get called forget get that control whether we can read the memory out and have to do the process with the input. Okay, and for the forget get, there is also another signal coming from outside of the memory cell to control whether the forget get can be open or not. If the forget get is open, that means we can read the original memory, and then we can combine the memory information and the input information. After this process, we then try to output the result. And there is also another gate called output gate. And there is a signal to control the output gate to determine whether we can output the result of this cell or not. Okay, so finally we can have some process with the output gate. We may be able to output the result of this memory cell. And we can see that this is a unique LSTM memory cell. And we can view it as a spatial neuron. It consists of 4 input. That is the input signal, the signal control input gate, the signal control forget gate, and then the signal control output gate. So it's kind of a spatial neuron. It consists of 4 inputs and 1 output. And how exactly does it work mathematically? We can view that. Assume we have the input signal Z, and then we first put the input signal to an activation function. So assume this is a sigmoid function, and after this activation function, we have the value GZ. And then for the input gate, another signal Z control the input gate. Okay, so this signal first we process it with an activation function to get FZ, and then we multiply GZ and FZ. Actually, this is FZI. Okay, so if the value of FZI is approximately 0, that means we will not consider the input signal. If the FZI is approximately equal to 1, then we will consider the input signal Z, GZ. Okay, and then assume that originally the memory information is C. Okay, we have a forget gate to control whether we will process C or not. Okay, so another control signal ZF is input to this activation function, and the FZF is the output of this activation function. That would be close to 1 or close to 0. If FZF is close to 1, then we will consider C. So C is multiplied by FZF, and then we sum these two values together. So we will get a new memory information C plum. C plum is equal to GZ FZI. This is from the input, and C multiply FZF. This is from the original memory cell. Okay, so we will combine these two values to generate new memory information C plum, and then we input the C plum to an activation function to get HC plum. And finally, whether we can output this value is controlled by the output gate. So the ZO is input to the activation function, and the FZO is approximately equal to 1 or approximately equal to 0. If FZO is close to 1, then we can output this value because the output A is equal to HC prime multiplied by FZO. Okay, so this is the whole LSTM neuron. How does it work? Okay, and activation function F is usually a sigmoid function. Okay, and so the output of the sigmoid function is some value between 0 and 1. Okay, it is used to mimic open and a closed gate. So this is the whole logic of LSTM. Let's take an example to show how it works. Assume that now the activation function here and here are just linear function. Okay, and assume the input value is 3, and the original memory information is 7. Okay, so first the input value is 3. Through the linear function, the output is still 3. For the input gate, assume the control signal is 10, and because 10 is a large value, so after sigmoid function, the FZI is approximately 1. Then we multiply 3 by 1, and then we get 3. Okay. From the cell, originally we have the value 7, and assume the control signal of the forget gate is 10. Then the output of this activation function is close to 1, and then we do 3 plus 1 multiply 7 to get 10. Okay, so the new memory information is 10. Okay, then we input this 10 to the linear function and get 10. Whether this value can be output is determined by the output gate. Assume the control signal of the output gate is minus 10, and because this is a very small value, so the output of the activation function is close to 0. So finally, the output is equal to 10 multiply 0. Okay, so the output is 0. That means after all this process, because we close the output gate, so basically we don't output anything in this case. Let's think about another signal. Assume the input signal is minus 3. Then after the linear function, we still have minus 3. And the input gate is open, okay, because the control signal, the value of the control signal is large. Then we multiply minus 3 by 1. Then we got minus 3. And assume the original memory information is 10. Then depending on the forget gate, right now the forget gate is closed because the control signal is quite small. So the new memory information is minus 3 plus 10 times 0. So that should be equal to minus 3. And then the minus 3 is go through the linear function to get minus 3. And right now the open gate is open because the control signal is large, is big. Okay, so the output is minus 3 multiplied by 1. So finally we output minus 3. So this is how exactly the LSTM cell works. And in the deep neural network, actually we don't we have a sequence of LSTM cell. Okay, we have thousands or 10,000s LSTM cell. So assume that at each cell, each memory cell, we concatenate all the memory cell, all information of the in-memory cell, and view it as a vector. So the CT minus 1 means the memory information from the previous times instance. And right now, at time instance t, we have an input xt. And actually, the input xt signal will multiply by 4 different matrices to get 4 different signal. Okay, the first signal is z. That is the original input signal. So the input signal, actually, because we take all signal into a vector form, so actually the input signal z is input of the first LSTM, the second LSTM to the n LSTM. We just concatenate together to be a vector. Okay, so by multiplying the first matrix, we get the input signal z. By multiplying by another matrix, we can get the signal zi, and actually zi is used to control the input gate. And there may be another signal called zf. Zf is used to control the forget gate. Okay, and remember we just concatenate all this signal into one vector. And also zo is used to control the output gate. So actually we have a sequence of LSTM. Okay, and basically LSTM, just like we mentioned above, in a hidden layer we may have thousands of nodes, and right now all these nodes can be repressed by the LSTM node. Okay, and such node has 4 input and 1 output. So just like we said before, the input signal after the activation function, we will multiply by the signal from the input gate. So here, the xt, we have the input signal z, and we have the input gate control signal zi. So we will basically zi after the activation function, we will multiply them together. Okay, so the output here is equal to the output here. And then we will consider the cell information, memory information. We will first check whether the forget gate is open or not. So here ZF is used to control the forget gate, and this is the control signal. And then we multiply the forget gate control signal by the memory information, multiply them together, and then we sum them together. So we sum the input, this is input, and this is memory. We sum them together, and then we input it to the activation function, and then determine whether we can output it or not. So the ZO is used to control the output gate, and we finally multiply this signal and this signal, and get the final output YT. So here is YT. Okay. So from this structure, we can process a given input by considering the memory information. And actually, the memory cell information will be stored as CT to be the process for the process of the next step. Okay, so this step is at time instance t, and this step is for time instance t plus 1. Okay, so actually the memory information will be stored, and then this information can be used to be the memory information for the next step. Okay, and actually we can also the memory information can also use to inference the matrix xt plus 1 will be multiplied. Okay, so we can also consider this information from CT to control or to modify the matrix where xt plus 1 should be multiplied. Okay, and also the output here can be also stored to be used to inference the transformation. st plus 1 should be used. Okay, so actually we can see many information propagation, information processing. And this is just a sequence of LSTM. And actually in a deep learning framework, we don't only just one layer. We have many layers. So this structure looks very complex because right here from this layer we have an output, and this output can influence the input of the next layer. And we can see we have a temporal evolution, we have layer evolution. So at the first time when many people see this, you will feel that what the hell do I read? Okay, what the hell do I read? This is too complex, so I will never implement it. Okay, however, don't worry about it. Okay, because don't worry about if you cannot understand this, because you can use some toolbox like Keras to do this. And actually, this structure is quite standard now. So right now, if you use when you claim in your study, you claim you use RNN. Basically, the standard way to implement RNN is this way. Okay, and if you don't use such complex structure, you have to specially identify, say that I just use simple RNN. I don't use LSTM. So every time when you say you use LSTM, that means no. Sorry. Every time when you say you use RNN, that means you use LSTM. You use such complex structure. And if you don't use if you try to simplify it, you may specially identify that you just use simple RNN, not LSTM. Okay, and there are several other variants called LSTM or GRU or simple RNN to implement the RNN structure. So after describing the structure of RNN, we now can go to the second step of the deep learning. That is to define the goodness of a function. The way to define the goodness of a function is actually similar to the convolutional neural network and the fully connected neural network. Okay, so taking the slot fitting application again. So the input is the sentence, like arrive Taipei on November 2nd. And the first input is arrive, the second input is Taipei, and so on. And the first word should be belonging to other, the category of other. And the second word should belong to the category of destination, and so on. So we can simply define the ground truth of each word, and then we calculate the cross entropy or mean square error between the output, the predicted value, and the ground truth value. So basically, the goodness of a function is defined similar to CNN and the fully connected neural network, even we implement it as RNN. So the final step is to find the best function. The way to find the best function is basically by using the gradient descent algorithm, or the so-called backpropagation through time algorithm. So every time we still need to update the parameter by considering the gradient. Okay, so this is the main concept. This is the big concept to do the optimization to find the best function. As we done in CNN and the fully connected neural network, we all use such algorithm. However, RNN learning is usually very difficult in practice, although we can use such algorithm to find the best function. But in practice, RNN learning is actually very difficult. Why? Because RNN-based network is not always easy to learn. Okay, and this is a toy example showing the numbers of epoch and the total loss. Okay, the relationship between total loss and the numbers of epoch. Sometimes when we are lucky, as the numbers of epoch increase, the total loss decrease smoothly, monotonically. However, sometimes when we are not lucky, the total loss would look like this. It seems that there is no standard, okay, and we cannot expect the value of the total loss, how the value of the total loss change, and sometimes the total loss will be very, very big, and when you learning, you will see the NAN, not the number. Okay, so in practice, we usually cannot very smoothly, very successfully construct or define the best solution of an RNN network. And why does this happen? The main reason is that the error surface is rough. Okay, it's not smooth. So the error surface is something like this. Okay, sometimes for some region, the gradient is quite small, and for some region, the gradient is quite large. For example, originally we may start from maybe from this point. Sometimes if we from this point, and then we may move to this point, and then move to this point, and at this point, because it has a very, very large gradient, so when we update the parameter, we may be multiplied by a very big value, so that we will jump to a very far away. Okay, so sometimes we will get an AN, or sometimes when we update, we may get very large loss. Okay, so in many years ago, most researchers cannot construct a successful RNN, and at that time, only very few researchers can do that. And actually, the only researchers who can successfully train the RNN is using a very simple technology called clipping. That is, for every time when the network try to update the parameter, we will check the the value of the gradient. If the value of gradient is larger than the threshold, we just set it truncate the gradient as a fixed value. Okay, this is called clipping. So this simple method is to avoid when we update the parameter. This is to avoid we will influence by a very large gradient, and we will update the parameter to a very large value. Okay, so the main reason of why why it is difficult to train an RNN is that the error surface is either very flat or very steep. Okay, it's quite complex, and we can also see why this happened. Okay, from a toy example. So in this toy example, this is a very simple toy example. The input is 1000000, and we just do such simple process. Every time when the input signal is coming, we multiply it by 1, and then through a linear function to output the value, and then we output y1. Okay, and we store the value in the memory. Okay, so at the second time instance, the input value is 0, then multiplied by 1, then we got 0, and we plus the w, and the w is 1. Is 1 here. Okay, actually it's w. Okay, because we may multiply a parameter w here, and then 0 plus w. So and then multiply by w, we got y2 as w, and then and so on. So imagine that we have 1000 input. So the final output of this network is actually w to the power of 999. Okay. In this case, let's imagine that how does different values of w influence the result. If the w is equal to 1, then the y1000, the final output will be 1. If the w is equal to 1.01, then the final result will be around 20,000. Okay, so when the output is very large, we will get, in the process of the gradient descent, we will get a very large gradient. Okay, we will get a very large gradient. So in this case, we may want to set the learning rate to be very small because the gradient is quite large. However, when the w is equal to 0.99 or 0.01, the final output is approximately 0. So we just change from the w from 1 to 0.99 or 1 to 1.01. The final result will change a lot, and the gradient value will also change a lot. And when the gradient value is quite small, we may like to set the learning rate to be large. So sometimes we need to set large learning rate. Sometimes we need to set small learning rate. And this is all depending on the slight change of the parameter. Okay, so this is why it's difficult to find a converged optimal solution from the RNN structure. So how can we solve this problem? There are some helpful technology. One technology is actually the LSTM. Okay, LSTM can LSTM can deal with gradient vanish problem. Okay, the main reason is that there is a design called the forget get. Okay, so we will add the input signal and the memory signal. Okay, and for any time, and in the original design of the LSTM, there is no forget get. Therefore, for any input information, the information will be accumulated in the following process. Okay, and sometimes the bad inference will propagate again and again. And because of the design of the forget get, sometimes we can eliminate noisy information or bad information. Okay, to influence the whole RNN. Okay, so actually, the most state-of-the-art LSTM can deal with the gradient vanish problem because the inference never disappear unless forget get is closed. Okay, so if forget get is open, we can avoid the gradient vanish problem. Okay, and actually there are also some other variants to solve this problem. Although this is still an ongoing research topic. Okay, there are still some. There have already some simple method to avoid or to successfully train RNN. One is LSTM. Another one is called gate recurrent unit (GRU). Okay, it's simpler than LSTM. GRU. The idea of GRU is that we correlate the parameter of input gate and forget gate. Okay, if we open the input gate, then the forget gate may be the inference of the forget gate may be decreased. Okay, and if you are interested in some details, please refer to the paper. And there are also many other variations to, but it looks quite complex. Okay, there are also other variants for us to do to construct the RNN. Okay, and if you are interested, you can refer to the detail of the papers. At the end of this lecturing video, we will give you more applications. As we said before, we first use the slot filling application to talk about the RNN. Okay, and the input of the slot filling problem is a sentence. Okay, for example, this sentence consists of 1, 2, 3, 4, 5 words, and the output of the slot filling application, slot filling system, is the probability of each word belonging to each category. So if we have 5 input words, we will have 5 output probability. And this is what RNN can do. However, input in this application, input and output are both sequenced with the same length, but the RNN can do more than that. Okay, RNN is actually very general and can be used in many applications and problems that are involved with the temporal evolution and memory. For example, RNN can do the problem related to many to one. For example, sentiment analysis. Okay, we may want to analyze the review comment of a movie, and then we try to output a value that indicate how likely or how funny, how interesting of the input movie of a movie. Okay, so the input of sentiment analysis may be an article, and in this article there are many words. Okay, and we can model the relationship between these words, and finally output the degree of interestingness or the degree of highlight of this of this movie. Okay, so this is a many-to-one mapping. The input is a sequence of words. Okay, and the length may be varied. Okay, and the output is just a real value, and this real value indicates how interesting or how funny or how important of this movie. Okay, so we can do many-to-one mapping. We can also do many-to-many mapping. Okay, but in this case, the output is shorter. For example, both input and output are both sequence. Okay, but the output is shorter, like speech recognition. So in speech recognition problem, the input is an audio signal, and the output may be a character sentence. For example, when I say this is good, okay, and we input such signal to the RNN, and then the RNN will output for each time instance. This RNN will output, for example, it is good. Okay, we may output many results, and finally we will do some trimming, and then get a characteristic character sequence. Okay, so for example, when I say understanding, there are many symbols. There are many symbols. Okay, there are many symbols in the audio signal called understanding. However, the output of this audio signal may be just one English word. Let's call understanding. So we can do many-to-many mapping. We can do also other many-to-many mapping, like sequence-to-sequence learning. A canonical example of such learning is machine translation. So we may try to input, for example, an English sentence called machine learning, and in Chinese, we call it 机器学习. Okay, and the length between input and output may be varied. Okay, sometimes the length of the English sentence is longer. Sometimes the length of the Chinese sentence is longer. Okay, and the RNN has no limitation to do such transformation or recognition. Okay, so we can do many-to-many recognition. And you may think about because RNN can continuously output the result according to the memory information coming from the previous time instance. So when we input machine learning, then the output may be, for example, 机器学习 and so on, because we will keep processing the memory information from the previous time instance. So maybe starting from 习, then the following word we may output 冠, and then given 冠 we may output 信, and so on. So a very typical simple RNN, we don't know how to stop. Okay, we will keep processing it, and the solution is actually simple. Simple, and we can add a symbol. We can add an end of sentence symbol to do this. So given such information, we may output 机器学习 and then output the end of sentence symbol. We can also use RNN to do one-to-many problem. For example, input an image, and we output a sequence of words. And this is a very famous research topic in recent 2 years. Okay, starting from 2014, 2015. There is a very important research field called image captioning, or caption generation. The input is an image, and then we can input this image to a CNN model so that we can extract important feature. So we can represent the image by a vector, and then we input this vector into an RNN, and then this RNN will output a sentence describing the input image. So we may output a woman is playing frisbee or something. Okay, so this is a very important research topic in recent 2 or 3 years, especially in computer vision society. And we can do image captioning. We can also do video captioning. Okay, so given a sequence of video frame, we can output a sentence. To describe the input video, like a girl is running, or a group of people is knocked by a tree, and so on. So in the end of this lecturing video, we conclude that in this lecturing video, we mainly introduce 2 important deep learning framework. One is convolutional neural network, which is especially appropriate to describe visual information, image or video. And when we try to consider memory information, we need to construct a recurrent neural network, RNN, and we see there are many variations and important technical challenge of RNN.